Welcome back to our session on measuring information storage in information processing in complex systems. In this short video, we're going to look at using the JIDT toolkit to measure the active information storage from empirical data sets. The way we can do this simply is by using the auto-analyzer, which also has implementations for the active information storage contained there. So all you need to do is start up the auto-analyzer, select the active information storage option, and then you'll have access to all of the types of underlying mutual information estimators that we have. And the same parameters that we saw before for underlying mutual information calculators, we have the same parameters for the active information storage. For example, for the discrete calculator, we can set the base. For the KSG estimators, we can set the number of nearest neighbors, and so on. Let's have a quick look at that. Okay, so in my JIDT distribution, I'll double click the jar file again to start the auto analyzer, and now I can select active info storage as one of the auto analyzers to launch. Once I do that, we get access to all of the estimator types that we saw before. Here we'll just focus on KSG for our examples coming later. We can see a list of properties, many of which we already saw with the mutual information KSG calculators, and some new ones as well. Probably the most important one here is the K history parameter, which we'll talk about in the next couple of slides. So that K history parameter is very important because it is really the most important parameter for the active information storage, the history length that we consider from the past to look at how predictive that past is of the next value. And it's a key question, how should we set that parameter? For example, let's have a look at a very simple complex system, the elementary cellular automata rule 54 here. And we can think about computing the active information storage for any one of the cells in our CA here, or looking at the statistics across the ensemble of cells and computing the active information storage. When we do that, what should we set the history length K to? We know that only one past value of the cell has a direct causal influence on the next value. Should we set our history length to just one? I don't think that's the right approach because it doesn't align properly with our view of information processing and the way we model information processing in the complex systems here. Yes, that one value is the one that's directly causal, but we can find other influences from the past, for example, via feedback loops to other cells that provide that correlation from the past to the next value at a longer time length than just one. We know here in the CA that each cell is coupled to its direct nearest neighbors. Each of them are. So that means each cell has a feedback loop from its past to its future at an arbitrary long time length by going longer, by crossing longer and longer links through neighbors and then coming back. So what should we set the history length to? There's no obvious answer. So let's think about what our past values mean in this estimator. We've represented that before. By our notation here with the bold variable name, looking at time step n going back K past values. We can recognize this from a dynamical systems viewpoint as a Tarkin's embedding of the past state of X. Okay, we've seen Tarkin's embeddings before in related courses. Tarkin's embedding tells us when we're looking at a dynamical system that is some kind of multi-dimensional system, provided certain conditions such as those dimensions being coupled, if we look far enough back in the past at just one of those variables, we can take several past values and reconstruct a state of the system as a whole by just using one of those variables as the observable. And that's called a Tarkin's embedding. So we see here that provided we're going back into the past long enough, our pass vector here is an embedding vector of the underlying state of our variable. We can also use an embedding delay here, tau, and skip over tau time steps between each sample in our vector. Okay? Often we might write the notation without tau, implying that we're just using a simple tau equals 1. Now what we want to do, coming back to our key question of how to set the history length here, we want to set the embedding for optimal prediction of our next value. What that means is we only want to stop at some length k when going beyond that with another sample doesn't change our probability estimates on the next value x at time step n plus 1. Okay, so that's what we're representing here. What we're showing is a Markovian dependence at order k of our next value on its pass, but not beyond that. So that's what we want to find. What is that value k that limits the Markovian dependence from what we can see in the data that we've got? So let's think about the competing concerns here. We want to have k as large as possible to capture all potential memory in the variable. But increasing k increases our exposure to undersampling, which we saw in our session on statistical significance and undersampling. There will be a sweet spot in between these competing concerns, either where future values from the past don't actually contribute to the next value, or where there is not actually enough data to validate their contribution. Okay, thinking again about how we can understand what we are able to measure given the data that we have. So we have 3 good options on how to work out what that history length should be. We can use the Rabbets criteria to minimize the prediction error from those past k values about our next value. The Rabbets criteria uses a k nearest neighbors approach for each past embedding and finds the mean of the corresponding next value from those k nearest neighbors of the past vectors. What it does then is computes the difference of that predicted next value to the actual value, and then takes the mean over all our samples and minimizes that prediction error with respect to the history length and embedding delay. We have this option implemented for you in the toolkit. I'll show you how to use that shortly. The second option to show you is to maximize the bias-corrected active information storage. We looked earlier at bias correction and taking out the mean of surrogates of our measure from the original estimate itself to create a bias-corrected value. Okay, so that's what this equation is showing. The suggestion of this option is to maximize the bias-corrected active information storage with respect to the history length and embedding delay. This approach implies that we keep including more points from history as long as they contribute more information about the next value than the increase in bias that we get due to the higher dimensionality of the space involved in our estimate. Okay, so we're going back further and further as long as those points keep significantly contributing to our measure of storage. Importantly here, for the KSG estimator, we must remember that bias correction is already built in, which helps us when we implement that under the hood for you. Okay, so that's another option that we have implemented in the toolkit. A third option is what we call a non-uniform embedding. What this does is to incrementally select points from the past which make a statistically significant contribution beyond those points already selected. Okay, this is a really nice way to set the embedding parameters. I think it's the best way to do it. Unfortunately, that's not directly implemented in JIDT, but it is included in our higher level IDT Excel toolbox from Vollstadt et al. Referenced below. But you have 2 good options there, the Rabbets criteria and the maximum bias corrected AIS. Let's have a look at how we can use those in the JIDT toolkit. We have, for either the KSG or the Gaussian estimators, an auto embed method property that allows you to turn this auto embedding on. Let's have a quick look at that in the toolkit. Okay, so you can see the auto embed method property here. From the drop down box, we can see that there are 3 possible settings for this. With the first setting, none, that means that we're telling the toolkit we're going to set our history dimension K and our embedding delay tau manually. So if I leave this set to none, we'll have to go in and set these ourselves. With our next 2 options, they'll get set automatically for us. So if I select Rabbets or Max Core AIS, they'll get set automatically, subject to the maximum search sizes that I set here. Okay, so we could say search up to size 10 and search up to a delay of 2, for example. And you can see all the details about those properties by hovering on them here in the GUI, of course. Okay, let's do one example here. We're going to select the SFI heart rate breath volume interaction data set, and we're going to set our embedding search dimension maximum to 10. Let's have a look at what happens if we do that. Okay, so we come in and we select the file that I just mentioned, SFI heart rate breath vol blood ox extract. We'll select that. We'll come in, we'll make sure our auto embed method is set to max core AIS. I ask you to set the maximum embedding dimension to 10, and we'll leave the maximum tau at 1 for the moment. Okay, now note here, I've left the manual values at 1. They will be overwritten inside the calculator anyway once we have selected an auto embedding method here. Let's generate the code and look at what happens when we run the computation. So we get our calculation made, and if we have a look into the code, we can see the properties being set to turn that auto embedding on. Okay, we've set the auto embedding method and we've set the maximum dimension we're going to search up to. What's also important, if you come back and look at the properties here, you'll see that our history length and our embedding delay have been now written back to the GUI for you. So we left that at 1 and 1. The calculation now set them to 2 and 1. So these were the optimal parameters found by the toolkit for us that are written back to the GUI here. So you can see those optimal parameters written back to the GUI. If you want to extract them in code, you can do so via a get property call on the calculator. And you can see more about that in the Java docs if you like. In our final short video of this session coming up next, I'm going to give you a brief introduction to one of the activities looking at measuring active information storage in cellular automata, and also tell you about a related measure of information storage being the predictive information.